All right, welcome to lecture 14. So lecture 14 is going to have three parts to it. Part A, part A, we're going to kind of keep talking about something we worked on last time in the 13th lecture, which is dealing with molecular formulas and empirical formulas. So we'll look more at that. So a few more calculations with moles, really. And then also in this video, we're going to talk about something called percent composition. So this video, yeah, there's a little more math, so hopefully you can keep a calculator handy. When we get to part B and C, there isn't any math. We're going to talk about something kind of different. We're kind of be done with a mole for a while at least. All right, so we got to spend a few more minutes looking at empirical formulas and molecular formulas. So let's go ahead and get into that. Okay, so just to remind you, the empirical formula, an empirical formula tells you the lowest ratio of atoms, the lowest ratio of atoms. But that doesn't mean that's the actual total, right? So the actual total, that was called the molecular formula. So the molecular formula is the actual number of atoms. Now, let me also tell you that the molecular formula, which is the actual number of atoms, it'll be some multiple of the empirical formula. I'm just going to write EF for empirical formula. All right, so for example, one empirical formula that exists is CH2O, one carbon, two hydrogens, and one oxygen. But there's lots of compounds in the world that actually have that as their empirical formula. So you see a list of them right here. Formaldehyde, acetic acid, lactic acid, all those are common, things. Formaldehyde is used as a disinfectant. Acetic acid's in vinegar. Lactic acid, that's what you get in your muscles when you exercise. So all of those, if we look at their formulas, you can see that they would actually simplify down to CH2O, right? Like, for example, for acetic acid, the actual molecule contains 2 carbons and 4 hydrogens and 4 oxygens, right? But if we take all those subscripts and if we divide by 2, you'd come up with this answer. And same thing for lactic acid. You notice how all those subscripts are divisible by 3. If you divide them all by 3, you'd come up with the same answer. So the actual molecule is going to be a sum multiple of this empirical formula. And there's lots of them out there. There's lots of different multiples, and all those are different substances, actually. So what we're going to try to figure out is, if I know the empirical formula of something, how can I determine which one of these options tells me the actual number of atoms? Which one of them is the total of the actual number of atoms? Is it twice as big as everything? Is it 3 times as much of everything, or 4 times? Or what's the multiple of that empirical formula? All right, so let's flip over and we'll do an example. All right, so for an example, this is going to highlight all the different ones. We'll just go through it. Oh, that's okay. There we go. Now we'll get to our example, I hope. There we go. All right, what is the molecular formula of a compound if it has a molar mass of 236 grams per mole and an empirical formula of C2H3O2? All right, what is the molecular formula of a compound that has a molar mass of 236 grams per mole and an empirical formula of C2H3O2? So what they really want me to figure out is, this molecule could in reality be twice as much of everything, so C4H6O4, or it could be like 3 times as much of everything, so it could be like C6, and if I multiply everything by 3, H9, and then I guess O6, right? So it's going to be some multiple of that lowest ratio. Now, how are we going to figure that out? Well, what they're giving me in this information is one big clue. They're telling me the molar mass is 236. So what's the molar mass again? The molar mass is the weight of all the atoms together, right? When we add up the numbers off the periodic table, the combined weight of all the atoms. So the real atoms together, their total weight is going to add up to 236. So with that extra little bit of information, you can tell me what multiple of this empirical formula we have in this compound. All right, so how are we going to do this? Well, the first thing we're going to do is, step one, we'll say, add up the masses in the empirical formula. I'm just going to write EF, okay? Add up the masses in the empirical formula. So I'm going to add up 2 carbons and 3 hydrogens and 2 oxygens. The atoms in the lowest ratio. Now, the weights I'm talking about, hey, those are the same weights we've been using, right? The 12 for a carbon, 12.01, the 1.008 for hydrogen, and the 16 for oxygen. So if you add that up, this is what you're going to come up with. I'm just adding up the atoms in the empirical formula. Let's go ahead and do it and see what we come up with. So you get 24.02, you get 3.06 from the hydrogens, and 32 from the oxygens. The grand total when you add them together, this is a 0 there. The grand total when you add them together, you should get 59.044. Does that look right? Oh, shoot, I blew it here. This should be, let me erase something here. This actually isn't 16. This is 24. Doing math in my head, I messed up. So yeah, it does out to 59.044. And then the units, I know often I've been writing grams equals a mole. You can also write grams per mole, all right? So the atoms in the empirical formula add up to a little over 59. Now what we're going to do with that is we will then divide the real weight of the atoms. What do we call the real weight of all the atoms? Oh, the molar mass. Divide the molar mass by this total to determine the multiple. So it's like one of these things where honestly it might make more sense just seeing it than writing it out. All right. So what I'm going to do is, in reality, all the atoms, they do not add up to 59. They add up to 236. So I'm going to take the total they should be, 236, and I'm going to divide by what I get from the empirical formula, which is 59. Now, when I do that, and I'm rounding just a little bit, just so you know, you basically get a 4. So what is that telling me? It's telling me the real molecule is as 4 times bigger, 4 times as much of everything as this empirical formula. So the empirical formula is like the reduced ratio. So yeah, there's 2 carbons and 3 hydrogens and 2 oxygens put together. That's the lowest ratio. But in reality, there's 4 times as much of everything. So what I would do is I would take the empirical formula, and I know it's actually just quadrupled. So it's not going to be C2H3O2. We're going to multiply all those subscripts by 4. It'll be C8H12O8. It's 4 times as big. And if you were to add up those numbers, it would add up to 236, all right, because that's what it's supposed to add up, the real weights. All right, so with that, all right, let's try another one. So I have to say, this can be a little confusing, can't it? Because you're like, have to figure out what to do and how to come up with it. So, you know, we're trying to figure out the real total number of atoms, like in this case, 8 and 12 and 8. So let's try one more. Let's try one more. Let me move on to it. All right, let's try one more. Let's try one more. All right, so it says, what is the molecular formula? So what's the actual number of atoms in a compound that has a molar mass of 181.44? So the real atoms together add up to 181. And the empirical formula, the lowest ratio, is C2HCl. So the real molecule will either be double everything or triple everything or quadruple everything. So what multiple is the real molecule? Now I know the real total of all the weight of all the atoms together needs to add up to 181. So the first thing I'm going to do is add up the weights of the atoms I currently have in my empirical formula. 2 carbons. Using the weights off the periodic table, right? 12. 1 hydrogen. Yeah, hydrogen's a little over 1. And 1 chlorine, 35.45. Now, if you add it all together, you got to double. Oops, no, I'm going to erase that. You're going to double the carbon. You're going to do once times the hydrogen and once times the chlorine. So I'm just adding up the elements that I currently have in my formula. They add up to, if you do it, 60.478 grams per mole. Now, the real atoms do not add up to 60. In reality, the weight of all the atoms together should be adding up to 181. So how does that happen? Well, there's either double everything or triple everything or quadruple everything. So the way you figure out how many times bigger this real thing is, the actual atoms are, you take the total you should be getting, or the total that really exists, I guess, 181, and you divide by what you have right now. Now, and again, I'm going to let you work this out to give me a little help here. Make sure you can get this. So what multiple is it? This molecule, is it twice as big, 3 times as big, 4 times as big? I'll let you work it out. Let's see what you get. Okay, you should be getting a 3 here. So you should have gotten 3. So what does that mean? It means the real molecule is 3 times as big as this empirical formula. All the subscripts should be tripled. All the subscripts should be tripled. So what is the actual number of atoms? What's the actual formula? Okay, hopefully you got that. Hopefully it made sense. All right, so with that, we're going to move on to a totally different kind of calculation. It's sort of the same idea, but kind of going backwards. So far we've been trying to determine formulas, and you've been starting off with like percentages or something. We're going to kind of do a problem that's sort of the other way. And the math is pretty drastically different. So let's try a couple out. All right, so let me go ahead and move on to that. All right, so one final calculation in this chapter, all right, and that's called percent composition. So percent composition, just to tell you what that means, it's the percent of the weight of a compound due to a specific element. So like we're going to do an example here with alcohol. So the formula for alcohol, you know, drinking alcohol, the stuff you drink if you're 21 or whatever, this is its formula. It's C2H5OH. So we write it that way. It has to do with kind of how the atoms are put together, their structure. C2H5OH. So let's say I wanted to know, like, in this molecule, how much of the weight of it is coming from carbon? How much of the weight of it is coming from carbon? So how much of the weight is from the carbon atoms? What percent of the weight is from the carbon atoms? So the way we would figure this out is we would basically figure out the weight of all the carbon atoms and divide by the total weight of the molecule. So if you want, there's a little equation that might help you to think about how to do that. So to find the percent of an element, it's going to be we have to figure out the weight of all the carbon atoms. So the way we do that is it's the number of the atoms that you have. So if we're dealing with carbon, it would be like the number of carbon atoms, which in that formula it's C2, so that would be 2, times the weight of that atom, divided by the total weight. So the total, I guess I could call it, the total molar mass. Now the only other thing you have to do is you have to multiply it times 100 to make it a percent. So to work this out, it's going to be the number of atoms of carbon we have. And, how many do we have? Look at the formula. There's 2. So it'll be 2 times the weight of a carbon atom. Oh, we've used that a bunch, or haven't we? 12.01. Carbon's a popular element. Divided by the total weight. Now, we haven't figured that out yet, but we know how to do that, right? You can add up the total weight of all the atoms. So it would be 2 carbons And how many hydrogens are there? Well, they're spread out, but you could still put them together. There's 5, and then there's another one on the end here. So there's actually 6 and 1 oxygen. So if you put it together, oh, carbon is 12. Hydrogen, I'm just adding up the molar mass. Hydrogen is 1. Oxygen is 16. I'll do this a little fast because, you know, you've seen this before, right? And then if you add it all together, for alcohol, it adds up to 46.068. You could say grams per mole if you want. I'm kind of leaving out the units because I don't have a lot of room here. All right, so that would be the weight of all the atoms together, 46.068. And then we multiply it times 100 to make it a percent. So how many atoms you got? 2 for carbon. The weight of that atom, a little over 12. And then that'll be the weight of all the carbons, really. And then you divide by the weight of every atom put together, the molar mass. So if you work it out, you should be getting 52%. So actually, if I go back to my drawing, my little silly drawing of this molecule, over half the weight is coming from the carbon atoms. Over half the weight, a little over half the weight. The rest of the weight would be the hydrogens and the oxygens and alcohol. All right, let's try one more. Let's try one more. All right, let's try one more. Oh, so we're going to move from one of my favorite or maybe worst addictions, alcohol. Ugh. All right, I'm not that bad. But, you know, I do an imbibe once in a while, to my other addiction, the one that gets me awake every morning. Oh, caffeine. All right, so it turns out I can do the same thing for caffeine. What percent of a molecule, what percent of, in this case, we're going to look at nitrogen. What percent of nitrogen, what's the percent composition, I should say, of nitrogen in caffeine? So what percent of the weight is coming from the nitrogen atoms? So to be able to figure that out, you really need to know the molar mass. You need to know the formula of caffeine. It's C8H10N4O2. So that's what a caffeine molecule, that's its formula. So the percent composition, I could ask you about oxygen or nitrogen or carbon, but just for the heck of it, I said let's talk about nitrogen. What percent of the weight of that thing is from the nitrogen atoms? So the way you find that is the number of atoms of whatever element we're talking about. Now, in this one, it's nitrogen, times the weight of that element, that atom, that element, however you want to say it, divided by the total molar mass, times 100. All right, again, I think it's really good for you to kind of be thinking through this, right, as I do it, right? You can't just watch a dude do chemistry. You got to be thinking about it, all right? So let's see what's going to go in every place for this formula. I'm going to ask it. We're going to do some pop-up questions here. What is the percent composition of nitrogen and caffeine? Number one, you need to put in how many atoms. What are you going to put in for the number of nitrogen atoms? Should be 4. All right, that's the subscript. Then, what are you going to put in for the mass of the atom? Okay, it's the atom that we're talking about, which is nitrogen. All right, so that should be 14. All right, and then you have to divide by the total weight. All right, so, we're going to bust out a calculator for this one. What's the total weight of all those atoms together? All right, think about it. Okay, let's do it. All right, so if you add them all together, 8 carbons, 10 hydrogens, 4 nitrogens, that's an H there, and 2 oxygens. All right, so I'm thinking it's going to add up to a pretty big number, actually. Let's see what you get. All right, let me work it out. So 8 times 12, you get 90, what's it going to be, 96.08, I think. And then 10.08 here. And then you're going to get, that's 28, I'm doing this in my head, 56.04. All right, and then 32. All right, if you put it all together, The grand total should add up to, all these guys, and shoot, I kind of ran out of room. It should add up to 194. Did you get 194? I hope you got 194.2. All right, so that's the number that goes on the bottom. And then, oh, again, I'm running out of room, times 100. So if you work it out, 4 times 14, that's the weight of really of all the nitrogens together, divided by the weight of every atom in the entire thing, it's about 28%, right? It should work out to be about 28%. So about a quarter of the weight is coming from the nitrogen atoms, a little over a quarter. All right, I hope that makes sense. So that's it for these calculations with the mole. We're on to something different. Oh, if you're tired of math, next chapter, no math. All right, so we'll be doing something else. So hang in there. If you're having any questions, please let me know. All right.